Last section of chapter 11 is looking at properties of solids. So when we talk about different types of solids, so this table that's also in your textbook is a great example and just kind of breaks down the different types of solids and some of the properties associated with them. So when you have a molecular solid, what makes it are atoms or molecules. And the forces that exist between the particles include London dispersion forces, dipole-dipole forces, as well as hydrogen bonding. And obviously, not all of those forces might be present, but some of them will be present. So some of the properties of molecular solids are that they're fairly soft, they have a low to moderately high melting point, and they are not very good at thermal or electrical conduction. Some examples of them include like argon gas or methane gas, sugar, solid sugar, sucrose, as well as dry ice. So in this, imagine the solid forms of those. It might be difficult to imagine the solid form of methane or argon, but you know, if you think of it, argon and methane have pretty low melting points. They're in the gas phase for the most part. So it varies quite a bit with molecular solids. Let's move on to covalent networks. So covalent networks are made up of atoms connected in a network of covalent bonds. So all covalent bonds holding it together, so that's the forces between the particles, are covalent bonds. And these are very hard, very, very hard compounds made out of covalent bonds. Um, and really high melting points, and it really depends on the specific substance whether it's going to have any type of conduction, whether it's thermal or electrical. Some classic examples would include diamonds, which is made out of just pure carbons covalently bonded to each other in a network, as well as quartz or crystals, which is silicon dioxide, same idea. And then next type of solid would be an ionic solid, and the forms or the unit particles that make up an ionic compound are positive and negative ions, so cations and anions. And the forces that hold the particles together would be electrostatic attraction, so positive being attracted to negatives. These tend to be hard and brittle. They have a really high melting point, and they are not very good at thermal or electrical conduction. So basic examples of ionic compounds include sodium chloride, calcium nitrate, and I mean, you can think of lots and lots of different ionic compounds that could fit this bill. And then the last type of solid would be a metallic solid, and these are made out of metal atoms. And you have the forces between them are called, well, you would have metallic bonds. Now, a couple slides from now, we'll talk a little bit more as far as what that means. But metals, metal solids are soft to very hard. It depends on the substance. You can have a metal that's very soft and one that's very rigid, right? That can hold up a bridge or a building. And they have low to very high melting points. They have excellent thermal and electrical conduction, and they're also often malleable and ductile. And malleable is the idea that you can pound it into sheets, and ductile is you can press it into wire. Examples would be just any metal element that you can think of, which there's a lot of them. Okay, so let's talk a little bit more about covalent network substances. So here we have on the left an image of diamonds. So diamonds are an example of a covalent network solid in which the atoms are all covalently bonded to each other. So that is why diamonds are very, very hard. They have a really high melting point because all of the carbon atoms are bonded to one another. Now switch over to the image on the right, which is a three-dimensional image of graphite. And graphite, which is made out of carbon just the same as a diamond, okay, so the stuff that's in your pencil is made out of graphite, and it's also a molecular solid, but this one is held together. So you've got these sheets that are held together by covalent bonds, but then the individual sheets of graphite are attracted or held together by van der Waals forces. So less, so you've got these layers or sheets that are attracted to one another. So when your graphite pencil goes across the page, these sheets of carbon are coming off in the form of graphite. And so the individual sheets are pretty strong, but the what's holding the sheets to one another is not nearly as strong because they're van der Waals forces. They're weak intermolecular forces. So they tend to be softer and have lower melting points. So I threw this slide in maybe last year, but so we're talking about different ways that carbon gets used. So if you think about, so you've got diamond, you've got graphite. So these are kind of the ways that you might find them in nature. So science has explored different ways that we might work with carbon that's unique or hadn't existed previously. So two images here. So one on the left are microtubules, um, and then you have on the right, you have a buckyball. So a buckyball is kind of where things started. Basically a large three-dimensional sphere, all of carbons covalently bonded to each other. And how this was explored initially is creating these buckyballs, but then placing atoms of different substances within that buckyball and seeing how they interact, what properties might come out of this kind of unique substance. And then on the left, you have these nanotubes of carbon. So rather than them being in a sphere or in sheets, basically have these just super small tubes of carbon atoms all bonded together in this kind of this lattice tube shape. And lots of really cool chemistry is coming out of the use of these tubes, these nanotubes. And everything from like exploring the potential of really super strong building materials to developing like artificial muscle, where when you put an electric current through nanotubes, they actually change their shape, they flex, so you could actually make an artificial muscle that would flex when you gave it different electrical impulses. So really cool, cutting edge chemistry is related to what are called fullerenes. And I really, if you're interested, definitely Google search it, read a little bit about it, because it's really neat chemistry, and there's some really cool stuff that's being done right now utilizing them. Okay, and then we have the idea of metallic solids. So metals, so they aren't technically covalently bonded. They are not covalently bonded to one another. They, but they do have stronger forces than your typical van der Waals force, so hydrogen bonding and all that stuff. And the reason why they have kind of this stronger attraction to one another is that when metals come together, so when you have solid metal, you have the metal atoms, but the outer electrons tend to be what are called delocalized. So the electrons can actually kind of move around the whole quantity of metal atoms. And this is why metals are such good conductors of electricity, is that in a solid form of the metal, electrons can easily move from one atom to another pretty readily. And so you can conduct electricity, do a variety of functions with it. So that's it, and I will see you tomorrow in class.